This is section 4.5. I am on page 7. The example says sketch the graph of f of x equals 2 times x squared minus 9 all over x squared minus 4. First thing is, what is the domain of this function? And the domain of our function is going to be all real numbers except for plus or minus 2, because that is where our denominator is equal to 0. And this, I should say also that this function does not reduce. So the domain is going to be all x such that x cannot equal plus or minus 2. And feel free to use different notation to write that. Next thing that we were supposed to find was vertical, horizontal, and slant asymptotes. So we have a vertical asymptote. We actually have two. And our vertical asymptotes are where the denominator is equal to 0, which is at x equals negative 2 and x equals positive 2. Our horizontal asymptote, you had a couple different ways to deal with this that we saw back in Unit 1, and one of the methods was to be using the pre-calculus approach, and I'll go ahead and do that. Since the exponent's degree is 2, and the denominator's degree is also 2, we have that they're equal, and to figure out our equation for our horizontal asymptote, we're going to have y equals the leading coefficients for those, which is 2 over 1, which just simplifies to 2. We have no slant asymptote because, again, slant asymptotes are going to be when the degree of the numerator is exactly 1 larger than the degree of the denominator. So once we've done that, we're going to go on and figure out our x-intercepts and our y-intercepts. So x-intercepts are where y is equal to 0. So if 0 equals and 2 times x squared minus 9 all over x squared minus 4. So if I multiply both sides by x squared minus 4 and divide by 2 and solve that, I get x is equal to plus or minus 3. So I have two values. I have negative 3 comma 0 and 3 comma 0. I'm going to underline those, and I'll underline my asymptotes also, so that way I keep everything easy to find. My y-intercept is where x is equal to 0. And when I set x equal to 0, we get y equals, and it's going to be 2 times negative 9, which is negative 18, all over 0 minus 4, which is negative 4. So this simplifies to 9 over 2. And so we have a y-intercept at 0 for x and 9 over 2 for y. Next thing was to find our critical values and determine where we have maximums, local maximums, and local minimums. So in order to do that, we're going to take a first derivative. The first derivative that we have is going to be the denominator times the derivative of the numerator, which would be 4x, minus the numerator, and I'm going to distribute through that 2. So we'll say 2x squared minus 18 times the degree of the denominator, which is just going to be 2x, all over the denominator squared. From here, I will multiply this all out, and we end up with 4x to the third minus 16x, and then minus 4x to the third plus 36x, all over x squared minus 4 squared, which again is going to simplify, so keep simplifying this, makes it easier to find our critical values. And we end up with negative 16 plus 36 is going to be 20x, all over x squared minus 4 squared. And so in order to find our critical values, we're going to set this equal to 0 and solve. When we do, we get x is equal to 0. And then we also need to figure out where our derivative was undefined, which is at x equals plus or minus 2. But x equals plus or minus 2 are not in our domain, so x equals 0 is our critical value. From here, I'm going to find my second derivative. So looking at your first derivative, let's scoot over here, and we'll find our second derivative. So we have the second derivative of x. is equal to. So we have our denominator from our first derivative, which is x squared minus 4 squared, times the derivative of the numerator, and the derivative of the numerator is just 20, minus the numerator, which was 20x, times the derivative of the denominator, which we have to use the chain rule, so it's going to be 2 times x squared minus 4 to the first, times the derivative of the inside, which is going to be 2x, all over x squared minus 4 squared. So I'm going to go ahead and put that to the fourth power. And if you notice, we have x squared minus 4 in both my terms in the numerator and in my denominator. So I'm going to go ahead and cancel one of those out. It makes it a little bit easier to deal with. And then from here, I'm going to just go ahead and simplify this. So we have 20x squared minus 80. And then minus, and we have 20x times 2 times 2x, which is going to be 80x squared, all over x squared minus 4 raised to the third power. Simplifying this even further, we get negative 60x squared minus 80 all over x squared minus 4 raised to the third power. And so we have, from here, to find our possible inflection points, we're going to set this equal to 0. When we do that, we get negative 60x squared minus 80. And then going ahead and solving this equals 0. Adding 80 and then dividing by negative 60, we get x squared equals negative 80 divided by, 80 divided by negative 60. Taking a square root on both sides, you'll realize that that does not work. We cannot have a negative inside a radical, so that's not any possible inflection points there. So we'll go ahead and cross that off. But we also need to look at where our second derivative is undefined, which is where our denominator is equal to 0, which is that x equals plus or minus 2. So the only thing is that this is not in the domain, so these cannot be inflection points, but they could be where the inflection is still changing. So next thing that we have is we're going to go ahead and set up a single number line. And our single number line, we're going to look at the first and the second derivative. So I'm going to go ahead and draw a number line here. I'm going to put in my critical values. And the critical values that we have are at 0. And then we also have possible changes in concavity at plus or minus 2. So I'll put in negative 2, at 0, and at positive 2. And then I'm going to go ahead and put some lines in here to kind of break up the intervals to keep track of everything. And then we'll put in the first and the second derivative. So we have our first derivative and our second derivative. So you have to pick test values in here for each of these. You have a second derivative, and your second derivative is over here. I want you guys to realize that the denominator is always going to be positive. So the numerator is what determines what sign this is going to have. And so when you substitute in something smaller than negative 2, if you pick a value less than negative 2, say negative 3, you're going to end up with a negative value, which would be decreasing. Again, if it's easier to pick something like test negative 3 and substitute that in. Something in between negative 2 and 0, if you test negative 1, that is also going to be substituted and we get negative, so that's decreasing. And then from 0 to 2, it is a positive value. So if you were to test negative 1 here and test 1 here, And when you substitute that in, you're going to get that it's increasing. Likewise, when you substitute in something else positive, you're going to get that it's increasing. And again, some of us feel better if we actually can plug in a number. Just pick a value in that interval to test. Okay, so the next thing that we're going to do is we're going to look at our second derivative. The second derivative was up here. So here's our second derivative. And these are the values I'm going to be testing in there. Same intervals again. So if I substitute in -3 into my second derivative, which is boxed right up above, I am going to get a negative value, which is going to be concave down. Again, test that on your own to see. When I substitute in 1, I'm going to actually get a negative over a negative, which will be positive, so concave up. And then again, if you test +1, you're going to get concave up also, be positive. And then that last interval over here, when you substitute in 3, you will get a negative value, which will mean it's concave down. So from here, we can figure out where we have any local minimums, local maximums. So looking at this, it goes from decreasing to increasing at 0. So that means we have a local min, and our local min is going to be at 0, f of 0. And when you substitute in 0 into your function, you get 0, it's 9 over 2 or 18 over 4, whatever way you want to look at it. And then if you wanted to write this as a mixed fraction, we're going to end up with 4.5. And we need to use all the information that we have, and we're going to graph it. There is no local maximums. Should write that down. And again, we do have changes in concavity, but they are occurring at -2 and at +2. And if you remember from earlier in the problem, those are where we have vertical asymptotes. So the concavity changes, but those are not considered points. So on here, we have a bunch of stuff to put on our graph. The first thing is, if we look back up here at the top, I'm going to put in my asymptotes. I have 2 vertical asymptotes and a horizontal asymptote, and I'll also put in my intercepts and local min. And we show vertical and horizontal asymptotes with dashed lines. So I'll go ahead and put those in at +2 and at -2. And then we have a horizontal asymptote also, and our horizontal asymptote was at +2. Okay, then we had x-intercepts at -3, 0, and at +3, 0. And then we had a y-intercept at 0, 9 over 2, which was the same as 0, 4.5. Okay, so those are all the values that we had to plot. That 0, 4.5 is also our, not only our y-intercept, but also our local minimum. So from here, I'm going to go back up and look at our sign chart that we had. And let's look at how the graph would look for each of these intervals. So we have the first interval is decreasing and concave down. So something along these lines. And then we have a decreasing function and concave up. An increasing function and concave down, or concave up, decreasing, concave up, increasing, concave up, and an increasing and concave down. So using that, we're going to sketch in the rest of our graph. And remember, the graph is going to approach, but it never goes through these asymptotes. So I'm going to go ahead and put in my, as we're approaching -2 on the left, it goes down to -infinity. And then as it goes off to -infinity, it's approaching -2. And then in the middle, if you notice, it's making almost like a U from that minimum, and then approaching those vertical asymptotes that we would have. And then that last interval, which goes from 2 on, is increasing and concave down. So again, putting those lines in.